You have it? Yeah. Oh. Okay. Right. Okay. So there's lots of filter possibilities. Very relaxed time. I won't try out if you want. So let's do that. Hardly works on my laptop. In 10 years, the next this generation will be able to do what it
yeah, you just wrap the live signal
I wonder whether this is set up a little bit of data processing is needed, and it's only got the count, which is a bit slower. So writing down the stuff. But anyway, I'm going to try that out. I really want to start passing out. I looked at the commercial ones that they start at 800-900, which is not too much. But anyway, I could build my own stuff. It's better.
Hello. Hi.
So
Louder. Louder. Okay. Hi. Here we are. We have the workshop today. It's a 4-hour workshop on digital musical instruments, digitally fabricated musical instruments. And my name is Alex. Okay. So. My name is Olivia Kotsifa from Cardiff Metropolitan University in the UK, and I'm here to present the team, and I'm going to talk to you about who we are. We'll make a very brief presentation of what digital musical instruments are, digitally fabricated ones as well. We'll talk about the Industrial Revolution, what's so-called the Fab Labs. And I'm presenting you Alexandros Kotogeorgakopoulos from Cardiff Metropolitan University as well. He's a senior lecturer in sonic arts, music, science and technology. Aris Bezas, he's a PhD student, soon to be doctor at the Ionian University. Anastasia Pistofidou, she's the coordinator of the Fab Lab in Barcelona, trained as an architect, and I am an architect myself, and I founded the Fab Lab in Cardiff. The Fab Lab in Barcelona has been up for many years, 10 years more or less, and the Fab Lab in Cardiff, we're going to open it to the public next week. So I've got some A4 sheets here. I'm going to pass them around so that you can write your contact details and we can send you all the information or maybe part of the presentation if you like. But before I do that, I wanted to talk to you about why we're here and how come we collaborate with each other. So the four of us are part in a European Art, Science and Technology Network. Which is what the theme of our European program is. Within this program there is 5 institutions from 5 different European countries. Of course, Anastasia in Barcelona and Fab Lab is one of them. We in Cardiff are the UK partners. Aris is from the partner team of Ionian University. ZKM is the other partner, and who did I miss? And Acroy, of course, from Grenoble, with Claude Cados, who's the coordinator of the European, and with some music with Miguel Laskim. So all of us, we are part of this European project, which has lots of resident artists. In fact, Iris and myself are resident artists as well, and this is what shall I say, an attempt to show what we can do through this collaboration. We're gonna talk about briefly the whole culture of digitally fabricated or digital musical instruments.
Shall we start?
Shall we start? Okay, let me just pass this around.
Okay, so hi again. I'm Alexandros from Cardiff School of Art and Design. So we're not gonna do a big presentation. It's better to start doing things together. Actually, this workshop was meant to be for 10 participants. I can see more than 10, because it's hard to put our hands and get our hands dirty with the technologies and the stuff we're gonna develop. But we will, you know, we can improvise and we go together. So 2 days ago, I gave a talk about digital musical instruments and digital fabrication. I'm not going to repeat my talk. I'm not going to focus on 2 points which are necessary in order to understand what we're trying to achieve and what's happening in this area. So I will start with 2 definitions. The one is coming from Wanderley and Miranda in their books about new digital musical instruments, where they define what it is. So I can read, you can read them too. And an instrument that uses computer-generated sound can be called digital musical instrument, DMI, and consists of a control surface, or a gesture controller as we call it, which drives the musical parameters of a sound synthesizer in real time. On the other hand, digital fabrication is about processes coming from the computer that use computer-controlled tools. So the tools are commanded by the computers. There are various tools that can do this job. Today we brought one which is, it's becoming, there's a buzz about this. We have, as you can see, 3 3D printers. We will talk more extensively about them. So these are the 2 definitions. And I concluded my talk on Tuesday by presenting this synoptical diagram. So far, we had 2 block diagrams in the digital musical instruments culture. So we had the gesture acquisition part, which is programmable. You can connect microcontrollers, program them to get signals from sensors and map them to a synthesizer, which is again programmable in the computer. And the synthesizer can be, you know, compiled or programmed in various environments: C sound, Max MSP, Pure Data, Super Collider, whatever. Today, we for the presentation and the demo, we're going to use Super Collider. But there's a 3rd part in this chain, as you can see, which is the digital fabrication stuff and part. So it consists actually an extra phase in the development of these new digital musical instruments, which is about programming the interface and also programming the affordances of things. So now we can very easily, quickly have a design of a physical structure and print it in a couple of minutes or hours, I hope not days, to, you know, to plug our sensors there and have an ergonomical interface according to our needs and our custom ideas. So that's the very, very brief introduction. But it would be nice to understand a bit about the Fab Lab culture and what consists a Fab Lab. So I think Anastasia and Olivia, they are good in presenting these ideas.
Okay. So what are the Fab Labs? The name stands for fabrication laboratories. They are spaces with loads of machines that are controlled by the computers. Machines such as the 3D printers, laser cutters, CNC milling machines from very big size, large scale ones to micro milling machines, 3D scanners, what else? Electronics, programming tools. So it's a space with all these machines, but it's not just a space, it's also a culture and it's also a network as well, which is what makes it unique and very very important in the new, what we so-called industrial revolution. Do you want to talk about that?
Okay. It's not very easy to talk about the industrial revolution. But during the first industrial revolution, we had extreme growth in the textile industry because of demand. So we had machines being fabricated in order to produce. And during the second industrial revolution, we had what we call the mass production. So the Mainly they were inventions of like electricity, of the rail, and during the second industrial revolution, and all this mass production led to an extreme production without sense. Nowadays we are talking about the third industrial revolution. The third industrial revolution is having to do a little bit more, it's related about the maker culture, the way that we should reconsider how the things are made, and having our customized local production, small scale, in our laboratory next to our house. So we have to rethink a little bit about the ecological footprint as well, and think about the fact that we should ask from the products what we want them to be, and not being served by being provided by products that they exist in the market. So, yeah, sorry. Yeah, this is like an image of the Edward Valentinsky. He's a photographer, and he has a very nice work which is called Constructed Landscapes, talking about the mass production in the second industrial revolution. So during the third industrial revolution, we have the peer-to-peer communication, we have internet, we have, yeah, as you can see the picture on the right, we have from the computer to the machine. And this is like a little bit of the state of art of the third industrial revolution. And this revolution is happening right now, and you are facing it. And in all the fields we should like rethink the way we fabricate, rethink the way we consume. So we talk about an open source design, an open source culture. We don't have we are not favored on patents anymore. We share our knowledge, and through peer-to-peer knowledge we can have innovation, because innovation is being conducted in a very fast way nowadays. Open source software like Arduino, and open source hardware like furniture that you can fabricate in any place in the world by downloading them. And all this is manifested in a way inside an environment like a Fab Lab. The Fab Lab is not that it is all the machines, because machines, they are also in the industry. The difference is that the machines are very easy to use. So they are very friendly to the user and somebody that doesn't have any knowledge from before. And so today we would like you to use these machines. And these are some examples of what one can make in a Fab Lab. So you can make from tiny things, you can make a software, you can make a microcontroller, you can fabricate your PCB board. But you can also make a solar house. This is a solar house that was fabricated in Fab Lab Barcelona for the solar decathlon. It is self-sufficient, and its form is done by using a software that is according to the place. So you have like the sun orientation, the air, and the form is being generated. It's generative by the location. And also, nowadays, it's very important to talk about how all this technology is revolutionizing the facilities that they are low cost nowadays. So we talk about prosthetics. We talk about that nowadays you can have your hand printed for people with disabilities for more or less like 100, 200 euros. And back 5 years ago, you had it for 3,000, 4,000. And this is the environment of work. Mainly, it's very important to say that we share the knowledge, so there is a very a big importance in the community, I am talking with Cardiff, we share the files, I send files to Africa to be 3D printed directly. And this is the network. The network is 10 years now that the Fab Lab was implemented in MIT in Boston by Neil Geshenford. And it was like a big success. It's an expansive model that nowadays, after 10 years, we have 250 Fab Labs in the world. 311, so it's still counting. And we are... Yes, Neil Geshenford. So what we do in the Fab Lab, we connect every Wednesday by teleconference system with MIT, and we have distributed knowledge. We have classes that they are conducted in all over the world by Neil Geshenford during the same time, and we also present our projects through the teleconference system. So we are also talking about open education. Yeah, so for example, Alexandros and Olivia, they came to Fab Lab Barcelona to do 2 exercises, and then they can, if they are in Amsterdam, they can also go and continue their work while they are doing their trip, for example. So there are different projects that one can do. Mainly we say that we don't do normal projects, we prefer to have like weird projects. And this is the new Fab Lab in Cardiff. There was an amazing job done by Olivia and Alexandros. And this is an interesting case for me, because I am in the Fab Lab Barcelona, which is quite like pioneer in Europe, in the European world. But the interesting case about this Fab Lab is that it has also the old tools, the old machinery. So we imagine that we combine the new digital tools with also like normal carpentry or normal processes like silkscreen printing or like old machinery. And we try to make this transition, and we try to find how the industry is going down nowadays, which are the factors that we can save and we can renovate and we can transform the industry. And now we can talk about this today. We have different applications, but we are interested in innovation in digital musical instruments, and Alexandros will continue.
Thanks. Again, I'm going to show some project that I presented them 2 weeks ago, but 2 weeks, no, it was not 2 weeks, it was 2 days ago. What? Yeah, it's about, I think it's about time to play something before I start talking about. So, let's listen to some music from Aris with an instrument that we fabricated. It was designed and fabricated in Cardiff, then we refabricated in Barcelona.
Excuse me. We also fabricate, we make a replica of Caval, this one. I'm not a professional player.
Come closer to the microphone. So when we started this work at Fab Lab Cardiff like 1.5 years ago or 1 year ago, we started doing a lot of parallel projects, always working with Haris, who is from Ionian, the audiovisual department in Corfu. So he came to Cardiff as a resident artist, and we started thinking about how we can do a Caval, which he didn't play the Caval right now, he played the ney. And we started making the Caval. Aris made the measurements. With the help of Olivia, they started doing the CAD drawings and started printing it. We were thinking about how augmenting its functionality with electronics. And at the same time, even before, there was another project that I was responsible for the Cardiff team, which we did it in Bristol, and it was about ney. Again, a traditional musical instrument, and we wanted to visualize the performance. So we augmented the functionality of a ney with sensors, capacitive sensors for the touch, and breath sensor, breath sensors for the flow and the breath, and also microphones to do some Fourier analysis, and from the Fourier analysis extracts things like the centroid and other characteristics important for visualizing the performance of the player. But there's been also some work done on other institutes, like this guitar, which is not augmented, it's just an electric guitar, and the designs, the cards are available. If you go to Fab Lab Amsterdam, you can get them, and if you have access to a CNC machine, you can start making this guitar. It's a bass guitar, which I played it when I visited them in Amsterdam, and Alex is a very friendly person. So we have other projects from, embossers, as we can see, the Technical University in Delft, or saxophones from companies. We have companies now printing things, like guitars. And more also research-oriented projects like the flute by Zoran in MIT, the Media Lab, where he also measured the acoustic response of these instruments, and he's tried to do a better understanding of how they perform actually those instruments. Okay, we're going to play the video, let me finish. And we have a fiddle also by independent people around the world. So Anastasia reminded me to play a video.
Also, I would like to mention how difficult it is to create your own instrument. In fact, with the software, I can speak loudly if everything is okay.
I feel...
Okay. So it's,
you know what? For the video,
okay.
you need the microphone.
It's like software. When you create your own software to make your own instrument, is mainly when you play an instrument, you buy an instrument. You buy a violin, you buy a caval, you buy an A. And so with this process, you construct your instrument. And after that, you can make changes. So you can change passe-pareil, you can change the whole, you can change depending on figures, how you feel it, the instrument. So it gives you a big freedom in the construction. And it's very easy. Yes, it's all open and all free. I designed it with FreeCAD. It's a new CAD software. Until now, it was too difficult to find an open source software for CAD. And it's reliable. After that, Arduino open hardware. The sensors were very cheap. We use a coil and copper to send the figures and how the hole is open and closed. You have the video?
I have the video.
Yeah.
I have more videos. There are a couple of videos to show, but I'm not going to show everything. This is the work done at my MIT. It's always hard. I hate this mic.
The 3D printed flute is a research project in the MIT Media Lab. Our goal was to create a flute using 3D printed technologies, a flute that is compatible with a traditional concert flute both acoustically and ergonomically. This flute is composed from several materials. A rigid material was selected for the flute's body, a different one for the mouthpiece, and a soft material for sealing the air properly. Only springs were added manually later. This project was fabricated with the Object Connex machine, which can print multiple materials in a single build. The overall process took around 15 hours, creating 4 separate parts that then were assembled to a working instrument.
So the video is online, so I don't want to spend more time. I would like to continue with other projects.
May I ask a question?
Already?
Yeah, just to know, what is just the material cost of producing that object? Let's say all the machines are given. How much costs to print an object like that? I really like that.
€20? Yeah, so for example, the one we printed right now, the filament is a PLA, but we also printed it with Aris in ABS, which which is a synthetic plastic where the PLA is more natural, and it costs no more than 10-15 euros. That one. But of course, there's higher precision 3D printers that cost much more.
Okay, so this is the Caval. Can you show the Caval, Aris? Yeah. We measured and printed in Cardiff.
The old one, this is the new one that Anastasia printed in Barcelona.
And that's a beautiful thing that they reprinted it again in Barcelona.
Play again. No, it's not a big. Just arrived yesterday.
Yeah. Anyway, you can when we finish, we can start and touch them and see how they are.
So, like a little bit, the printers, they have some limitations, of course, according to their size. So you have to think about how you design in order to use one specific kind of technology. So in this case, we had a limitation in height for the Caval. You cannot print horizontal in this tubular system, so we print in like this. And it's the same concept like the Caval.
Yeah.
Okay, I continue. So this is the other project. I will show you the video. There is a more fancy video now online because we're demonstrating this work. The opening was yesterday in the Design Festival in London. So you can see a big team of people, a very interesting team, because John O'Connell is the head of research in Cardiff University and ethnomusicologist. So he gave his expertise into the DNA. He talked about the context, the culture, and everything related to DNA. We wanted to respect all this. We don't want to create new gadgets. We want to respect the culture of musical instruments and start thinking about the future and give a continuous flow over their trajectory in history. So, for example, as Ari said before, normally when you start playing ney, you make your own ney. So you get the reed and you start with hand tools, making your instrument, you go to your master, and then you start playing with him, he corrects you. So it's not like in Western music where you go and buy a standardized instrument. No, you make it yourself. So we wanted to create a ney, which you can make it and personalize its design yourself. So John O'Connell was the musicologist, I was in Cardiff and I was dealing more with the electronics and the interaction, and Mace is an interaction designer from Bristol. We created a software also for this. I put my name twice, very nice. I like me. I'm 2 times important. Aris Bezos is Aris Bezos, and he's an A player, and he also did the measurements and the construction. Stefan Goodchild is a creative coder. He worked with very fancy people. He even went with Queen to the United States to tour with them, doing the visuals. And Olivia Kotsifa, who did also fabrication. So here is the instrument that we demonstrated in London. And here is the video that I'll play a little bit. Perfect. Oh, I'm not going to play it. Yeah, the upper part is the fingering. So Kalia, who was part of the user experience test, she's a professional ney player, and she really engaged with the instrument and the quality of the tone she produced, and she was even thinking to use it in her classes because she teaches ney in London. So I'm going to skip this for after the break. And now I think that ideally we have 30 minutes before the break, and what's written in the proceedings, what we published online, was that if you had some time, you will download Rhino or the open version of Rhino on your computers. Have you done this? Who have done already this?
Who knows how to design in 3D or like programming design?
How many? 2? 3?
What do you mean?
Yeah, CAD design.
Three?
CAD design?
Yeah. So what's written in the proceedings is it to please download already before coming here the software. Who downloaded the software to do CAD? Nobody.
Who has software to design?
What does count? Sketchbook, something like that?
Yeah.
Is that vendor okay?
SolidWorks, Rhino. AutoCAD. Yes, also
Blender?
like the AutoCAD 1 to 3D, make, design. So they are open source programs with an application.
Everything. Don't use a CAD. Do it by your hand. MATLAB.
Everything from
No. Maybe we're in the wrong conference. Okay, so I think Anastasia will go through the steps, demonstrate how we design something before the break.
Yes, we will do half an hour only, so that you can see more or less how interface of 3D programming, 3D modeling is.
And then
Maybe during the break, people, because the internet connection is quite good, so people can download it. Rhino from
you can start download Rhino now, or whatever, yeah. We're going to do a demo on Rhino, and maybe if we have time, another demo, Aris.
Is there anything that runs on Linux?
Yeah,
FreeCAD.
FreeCAD.
runs on
Yeah.
Linux, yeah.
FreeCAD.
So we suggest you download FreeCAD or Rhino.
What's the difference? What's the difference between Rhino and FreeCAD?
What's the difference between C-Sound and pure data? I mean, they have the same scope, but the FreeCAD is open source and free. Rhino is made by company. Now it's in a beta version, so they still offer it for free, for Mac users only. And we'll do a demonstration on Rhino. I'll give the microphone to
Rhinoceros. So there are 3 ways to design, so you can use either. One way is to design from scratch. The second way is to download an open source file. So if you go online and you find like Thingiverse, for example, is an online platform where users, they upload their files and you can download them for free. And the third one is scanning. So 3 ways of designing: scanning, downloading, and designing from scratch. Then there are a lot of programs about designing from scratch. So, from Rhinoceros, www.rhinoceros. Rhinoceros 3D.
www.rhino3d.com. You'll be able to find either the trial version for Windows, which lets you use it for some days, and for the Mac users, it's a free version because it's still an ongoing work they're doing, so they give it for free. So it's rhino3d.com.
And for those that they don't want to download Rhino or they don't have a computer, if they have like a smartphone, they can download an application which is called 123D Design or 123D Make, 123D Catch. So it's like from Autodesk online application. You can make a 3D model by taking pictures with your phone. So you can walk on the street and say, I want the 3D model of this bicycle. I take all the pictures around, and then a 3D model is generated that you can tune, or you can change, or you can directly 3D print.
So, since this is a... yeah, please.
For people that they don't have so much experience with 3D design,
Yes.
It would be easier maybe to do the scanning. So,
We haven't prepared the scanning for this workshop, so we wouldn't...
Just information. What would you use for scanning, reasonable cost? Where would you
Okay.
find? And if you have an instrument that you want maybe to modify.
Yes. So if you have an instrument and you want precise scanning, nowadays you would have to direct to like a higher cost scanning. But if you want like to scan forms that you don't need so much of precision, like a body or like a room or outdoors, you can use the application which is called 123D Catch. It's from Autodesk and it's free. And you can also use a camera, a Kinect camera, and ScanEct, which costs like 200 euros. And the Kinect camera is quite more precise than the application.
If you take the picture of a room, you scan the room, I mean, practically where you can print all this? What is the... Yes, I can think of, you want to scan an ocarina and make the holes in different places. I mean, I speak for something so simple. No?
This can be scanned. This kind of object can be scanned.
Something that can be in smaller parts.
But then in the program you always can manipulate, no? You can scale.
You can print parts and then assemble them.
Yes.
That's the solution.
Even if you scan something, you can edit it.
Yes, because you don't have like a blank page that you start from scratch. You have an object that you can manipulate inside the 3D. Okay, I connect now.
I just want you to say, since we're in the ICMC conference and people like programming, there is also a beautiful environment which looks like it's a visual programming language, which looks like Pure Data or Max MSP. And Anastasia, it's called Grasshopper. It's only for Windows users, but it's easy to do parametric and programmable design. You will show also elements of Grasshopper because that's maybe something that you will find funky, because you have blocks and you interconnect them in the way you interconnect Max MSP objects. Who has ever used Grasshopper in this room? Who knows Grasshopper in this room? 1, 2, 3. Okay, just checking. Yeah, so, okay, Anastasia will explain how you can design something. So we pre-design some buttons, pads, knobs for pots for you, which you would like you to modify them or play with them. We will start probably doing this after the break, and then we will assemble them. We have 2 stations to work with them, with 3 breath sensors, 4 pots, and 4 FSRs, 4 sensitive resistors. And you can see, for example, here, we 3D printed also a case like this, and we have some synthesizer programmed for you, so we can do a party at around 3:30. And, yeah. Do you have other questions?
Maybe just generally. So let's say I have an idea and I want to work on a project that uses these 3D printers. Is FabLab like a network that I could apply to as an artist with a project and go for a short-term residence to realize it, or do I have to buy these machines myself?
You can buy the machines. They're not extremely expensive. They cost like a MacBook. Stop buying Macs and start buying 3D printers. That's a general advice.
So these was, for example, they cost £1,800, like 2,000 euros.
But
considering their lifetime and what they can make, I'd say it's good value for money.
And also Fab Labs, depending on the Fab Lab you closer to your city, they're spread around the world now. So you can go and they have online information about how you can have access. If you want some tutoring from an expert like Anastasia, for example, or Olivia, or if you know how to use the tools and you just pay for an hour to use a 3D printer.
Can I ask something?
But you can also go online and enter 3D hubs where each user registrates his printer at home, and he can offer you this kind of service. So if you have a printer, you just say, I have a printer, and then there is by local demand. 3D hubs.
What about open source printers?
Yes, they are open source. In the FabLab, we fabricate printers.
No. Open source. I have the list, and with $200 or $300, I can make my own. Are they dependable?
Yes, in the Fab Lab, we fabricate our own 3D printers as well.
And they are free, the cards.
It's possible.
These ones, they are commercial because we use them for services. But
Yes.
we make workshops where you can fabricate your 3D printer. You need 3 motors, an extruder, and rods.
And those 3D printers are reliable.
You suffer.
That says everything, eh?
Yes, like
Yesterday.
when I opened the box yesterday after the flight in here, everything was broken.
Yes. And it happened
And
to
then I
us
had
too.
to mount everything back again.
So we brought one from Athens, one from Barcelona, and one from Cardiff. The Cardiff one was not broken, but they had a problem. So we're panicking this morning. Probably you saw us in the cafeteria. That happened to Anastasia last night with her printer.
But they are very simple machines. The philosophy is very simple. So it has plastic behind, and it's the cable, and it has a capital bank that is going up and start from the upper, and this head is moving at 2 dimensions. And it's melt the plastic, so it melt a layer, and after it's going down and melt the other layers. So a layer, you make the object. So it's very simple philosophy. And all
It's an additive process.
And extruder and motors.
So you cannot print everything in the 3D printer. There are different kind of 3D printers. They are printers that they use. Okay, I talk 10 minutes about 3D printers. Okay.
Okay.
Five.
5 minutes about 3D printers. So the process.
You want to keep for your wife?
So the process is very easy. You have like a 3D object, and the 3D object is described by coordinates, and you import the 3D object into the software of the 3D printer. The 3D printer is using a conveyor, a slicer, that slices the model by layers. And what it sends to the printer is XYZ coordinates movement. You can write a script that has XYZ coordinates, send it as a G-code to a printer or a milling machine or a laser cutter, because they all use G-code, and you can run the 3D printer. You can compose music that can be directly XYZ coordinates for a 3D printer. Also, you can have the input of music that is, you're listening with a sensor, the music, and you are sending the movement.
They told me that there was a piece on Monday with a 3D printer. But I was not there.
Yeah.
Okay. I was not there. I would like to be there.
Let's do it again.
So performing now, we have 3. An orchestra.
So there are different kind of 3D printing technologies. This is called FDM, fused deposition modeling. But there are also like SLA with light, UV, ultraviolet sensitive light, with liquid resin. They are like the powder 3D printers, metal 3D printers, and like a wide range. This kind of 3D printing technology is the low cost. This is what it was the third industrial revolution. Because before, the 3D printing technology, it exists from the 90s, but it was only for military or medical reasons. And the cost was like 10,000, 100,000 euros. Now, you can find online a 3D print for 200 euros. So this is a little bit manifesto. This is about 3D printing.
Perfect.
Any questions about 3D printing?
I have a question. How did you do your piece? What did you do?
Oh, it was just composing with the form. So we actually went through the pickups on the screen. We live processed it. We have the sonics.
Okay.
It was a high level.
It was real time printing,
Yeah,
and you
yeah.
you were getting the vibration.
Yeah. That's a great simple thing to do. Just put a piezo on one of those, and then a good amplifier. Listen to all the low frequencies you can't hear.
give ideas now.
Yeah, yeah.
Thanks.
You can put a mic, contact mic as well.
Please, you mentioned a G code.
Yes?
Yes.
It's just a script.
Yes.
We said something about the filament cost like
G code. What does it mean?
The G code is like a text document. The processor of the software of the 3D printer, what it does, it translates a 3D object into a mechanical movement. You can,
Yeah, but it's a free structure.
and
Document is,
it's like a text document, XYZ coordinates. You can write. My project in IAC, in the Institute of Advanced Architecture of Catalonia, was to hack a milling machine and make a sand 3D printer. So we were talking about printing in the desert, in a big scale. Yeah.
You asked me a question, so you can Google the company. There are many companies that made this. This is Color Fab, and this is the filament. That's cost £25. But if you Google it, you will see they have a range of products. Color Fab with 2B. Color Fab.
This one you can print 3 or 4.
Color Fab is...
No, 3, 4 nails, even probably more. So there is a lot of material. Probably every print is not going to be successful. We had some funny byproducts, and we were trying to solve it. Aris basically was trying to solve it in my kitchen with a, how do you call it?
With my hairdryer.
Hairdryer. He was on the hairdryer trying to melt the filament because it was...
Is the process of translating a complex shape into something that is actually printable by the machine taken care of by some software? I mean, because of hollow shapes or whatever.
Yeah.
You cannot print
That's the problem with scanning, but...
So this is what we say before, that you cannot print everything. You cannot print everything, so you have to see what kind of model you have in order to know which kind of 3D printing technology you're going to use. If you have like you can print a chain directly, or you can print like a sphere inside a sphere inside a sphere with like Z-Corp technology, powder 3D printer. But with this kind of 3D printing technology, since it prints from down to up, imagine that if I want to print me, it's a standard example, if I have my hands like this, if I reach here, I will not be able to print my hand. So I either have to do this, or I have to put supports. So there's also the support material inside there. Like, these are very detailed. This is not the concept of the workshop, so I don't want to enter into detail.
That can, I was asking because again that can be a tough task, like to be able, if you cannot afford like the 1,100 machine that can print anything, and you want to print with this, the task of splicing, I mean making your shapes various parts so that you can print, so that you will print the arm and then the body.
Yeah, this is what... No, it is not automated, and this is what we say, that you have to learn to design in order to understand the technology. Because if you know how it works, then you will know what doesn't work and how to design. So it's like a loop. Okay.
There's a question. Yeah, please.
I don't want to interrupt if you need to continue.
It's a free form piece.
Since it's a kind of material, it's the same material, you probably have a kind of properties. Do you have a place where you can find like if it has vibrating properties, if it breaks after some point, if I want to do some kind of vibrating.
So you know the technical shit, no?
Yeah,
like the technical
but
shit.
more into acoustics or vibrational.
Of course, this is like ongoing research, and since this technology is thought to be open source, I think that the research is open.
That's what we're trying to do. So
But can I...
That's your job also, if you're interested.
Yes, sir. You also designed the inside design, so it's layers,
So we
that there is layers, the infill.
This morning we printed, and I'm going to share it with you. I don't know if this is going to stay after the break to do some actual CAD drawing. Who wants to stay and use the computer to do a CAD drawing? Let's count the hands. CAD 1, 2, 3, 4, 5, 6, 7, 8.
Fair enough. It's good.
What did you ask?
Not that everybody would leave.
Okay, yeah. So this morning we printed those two enclosures for the controllers. You can see that you can control the density of the material. So you can print faster or slower. So these are two cases. They're the same. They are made of but which one is yeah, low density is faster, much faster. We're testing them empirically.
Have you tried to print like moving parts, like gears? Or have you tried to print moving parts, like rotating parts?
It depends.
Like
Yes, they already make the motors.
Yeah.
And they last a long time?
I don't know that. I didn't try it.
Okay.
But they already make the motors, the rears, the gears.
I was thinking more about big gears.
Today they told us that they made already a car, 3D printed.
Okay. Right, that answers my question.
I made a human being.
And that's your limitation.
But also there are different levels of how hard.
Like flakes. There is also like an extra machine next to this printer that it eats the waste and then it converts it again into material to be 3D printed. It doesn't work so well yet. So it's like very interesting theme for us that we are inventing to discover this. No? And there is also like bioplastic. So you can make compost system and then create your own plastic with glycerin and sugar and things like that. And also like, okay, this is an important thing. This is a static object, but nowadays the research in MIT is more oriented to the programmable matter. So we are talking about shape memory, we are talking about materials that they have phase-changing properties. So like nowadays we are more into this kind of research. It's not like you program, but then after you program you have like the final outcome. But we don't want that. We want to have like something, an object that can be still programmable. So we talk about the programmable matter.
Can you please mention again the Android application?
Yes, 1, 2, 3D catch. 1, 2, 3D catch for scanning, and 1, 2, 3 design, and there is also 1, 2, 3D circuit for making circuits. So we are interested in having like an integral project. In the Fab Lab you can have your crazy idea, then you have to make sketches, program it, fabricate it, code it, make the PCB board, and like more or less than like your project about tangibility, that it was including all the things like the material, the PCB, the programming, the sound engineering, like an integral project. And we are multidisciplinary, and this is very important, that we learn different tools in order to be able to navigate with the different tools. Okay.
If I want to adjust some other material, could I pause the printing at some point and adjust other stuff and then continue the layering?
We will do that. We will do that. Yes, there are also, like, that printer there has double extrusion, so you can use like a material that is dissoluble, like that you can put it in the water and it dissolves. And so you can use like a double color, or you can use like a difficult print with dissolvable material, or you can use like the support with one extruder. And but also like they are like there is also a printer that is very nice that is multi-material. So in the same print you have like flexible, then you have rigid, and then you have like different kind of material. But these are still like a high cost, like 300,000. Yeah, it has been done like experiment, and it works, but it's like difficult. There's also like another experiment that was done is to print in angle, so like a structure that wouldn't stand, it would be standing because you had the printer in angle. Okay, τι μπορώ να κάνω, πείτε αυτό. Αυτά. Okay. So, this is the interface of Rhinoceros. We use Rhinoceros because it has this extension plugin, which is called Grasshopper. You can connect Grasshopper with Arduino, OSC. You can connect Firefly, take data from web pages. So we use Rhino because it has this plugin that is it's open source, the plugin. So there are people that they are coding in Python and VBScript modules, so that you can have like physics integrated, you can have like processing connected with the 3D modeling, or directly taking the value of a sensor and sending it to a machine through the interface of Grasshopper. So this is a main use. The people that they are more leaning to coding, they can use like OpenCAD, or FreeCAD. And they are like other programs that you can directly code and make the 3D. So this is the interface. The interface, they are like, it's very easy. So there is like top view, perspective, and front. And here you can say, okay, what I want to do, I want to do like a rectangle. And you write everything. So I can make a rectangle, and I say, okay, start from 0 and make a rectangle that is 20 by 20. Okay. So here my rectangle, and here I can see it in all the views. So after that, I will extrude my rectangle, and I say, okay, Olivia, this is 20 by 20. Yes, no? Okay. Yeah. So I say, okay, I make it 20 by height. And this is like a box. Of course, like you can say, no, I wanted to make a box, I just write box. And I can do a box directly. So there are many ways of designing in this 3D model. This is software. You can either navigate on the upper toolbar or on the left, or you can write. We prefer to write directly. Just automated. What I think, I just write it. And then I want the box to be solid, so I cap it. And then I want to twist it. So I write twist. And I want to twist it from here. And I can twist it a little bit, for example. Sorry. It's very bad, this screen, I think. So, here I have a twisted box. So, of course, you can record history in this program, and you can go back and forth. So, like, if you have, it's kind of parametric, but still not parametric. So, let's see Grasshopper. Grasshopper is the plugin. So, oh, this is very bad.
Grasshopper is the max MSP for the fabricator, designer.
So, I say, here I want a curve. Oh, and it's like very easy because it's models, but you can also write directly in VB script. I have this curve. And here in the real software, like I will make a circle in top view. So I make a circle. And then after this circle, I will just make copies of it. Copy. And I will make one up and one down. And then I will scale this, the central circle, to make it bigger, or even bigger, no? Better. Okay. So here I have a curve, and the grasshopper is green, so it says you don't have a curve, so I say set one curve. So I set one curve and it's green. And I do the same for all three curves, no? Curves. It's a basic tutorial, very fast, before the break. So this one, set one curve, and this one, so you see it's gone red now that it is in Grasshopper. So set one curve here. And then what I want to do is that I want to divide it. So I write divide. Divide curve. Mm-hmm. So this is the curve. Okay, I see. Okay. And I don't know if you see here. Okay. They are like this green axis. You see? So, it's like a number. So what if I make it dynamic and I put a slider, a number slider, that will have values from, like numerical values, not with zeros, from 0 to 50. Okay? Okay. And then I connect the slider to here. Okay, so what happens here is that you can generate a lot of different designs in only one design. So this is like we call parametric and generative. And I think that you all know it in your concept, in your context, and this is the designer context. So the thought is the same. And after that, I want to create arcs. So I write arc, but it's an arc that it is made by 3 points. So, okay, I take I have to divide all to take, sorry. So, divide. Curve and divide. Curve. It will be very fast. So, okay. So I take point A, point B, and point C. And here is my arc. So they're like a little bit weird. Yeah, because I should have taken point A, should be in the middle, and point B should be up. So this is more or less. Okay, so here I can play with the slider. And after the tutorial finishes, by making it, now it's only lines, so you cannot 3D print lines. You cannot 3D print 2D objects, you cannot 3D print an image. Mainly you can laser cut it or mill it, but in the 3D modeling, in the 3D printing, you need the object. So this is pipe, and I want this to become, I also want the curves to become lines. Okay, and so after I play a lot with this, I can also like define the radius of the pipe, and I finish like in 1 second. No, it's 1 minute. Sorry. So yeah, okay. I have like the radius of the pipe, so I can just make it fat or. Okay. So whoa. Okay, and now I want to 3D print it. That's what happens, no? That after I design it, I want to see how the physical object is and make corrections, and like it's the first prototype, fast, rapid prototyping. So what I would do, in this case, like if I try to grab the object, I don't grab anything. I grab only the first lines that I did in the beginning, because this is only visualization. It doesn't exist. So what I do is that I just bake it. And here's the object. So there are like some limitations in 3D printing. All the objects should be watertight. If I just drop the object in the water, water shouldn't enter in the object, so it should be like capped with like full volume. So I say cap. So it's like putting caps everywhere. And then I make a mesh, and then I say select only the meshes in this software, and then I say file, export selected, and I export it in the format that all 3D printers stock, which is stereolithography. So I put it in the desktop and I say ring. Okay? And then I just want to go to the software of the... I will do this after the break. Okay.
Alright, so I think we need food. So what time do we start again? 10 past?
Yes.
10 past. So see you all, I hope, or more or less, at 10 past 2.
Okay.
Yeah.
So it's good. It's less of you now because it's going to be easier to handle everything. to download the software. But what I wanted to ask was, if you want to have a go and print your so what we have printed out several cases with space so that you can 3D print your own knob, your own pad, and your own mouthpiece. So we have 3 different sensors here. We have potentiometers, we have pressure sensors for the mouthpieces, and we have FSRs as well. So the FSRs are going to be used for the pads, the potentiometers for the knobs and the breath sensors, the pressure sensors for the mouthpiece. So if you guys want to design your own knobs or pads or the enclosures for the mouthpiece and play your own instrument later on, because we've already connected stuff with the Arduinos and it's all ready to go. If you can come forward so that we know who's interested and we can help you out with the software. So even if you don't have the software downloaded, we'll try and, you know, between us, share our laptops and we can try and do it this way. So, yeah, let's see who's interested first.
And who has a computer?
And who has a computer? That's another question.
Yeah.
No, that's fine. We can use ours.
Probably will.
Are you good already?
I'll go running out and standing around.
Okay. Perfect.
Okay, so I was just saying for the ones who just arrived that if you want to have a go and design your own knob or pad or the enclosure for a mouthpiece and add it to the cases that we've already prepared for this workshop, if you're interested in doing so, if you can come a bit further down so that we know you are interested and we can help you out with Rhino or FreeCAD or AutoCAD or whatever software we can help you out with. Whatever software you choose to use.
So you are going to demonstrate it Rhino?
Yes, yes, yes. And
Yeah, so we have already set up some sensors and we have already some designs that we're going to explain to you how to do them, and we do it step by step, otherwise it won't be. We want to make it as workshopy as possible. But in order to follow us, you need a laptop with Rhino or to pair with somebody who has a laptop with Rhino. And FreeCAD, yeah, the same, yeah, sorry. FreeCAD is fine too. Yeah? You have a laptop? You're gonna play and mess around with? Yes?
Can I ask?
Stefania?
But are you showing the demos with Rhino or with FreeCAD?
With the Rhino, but we have also Aris who can help you with FreeCAD.
Okay, because I managed to download the FreeCAD, but Rhino is installed.
We're going to do both presentations. It will take a lot of time. We'll do it in Rhino, but it's similar.
I can make a short demonstration in FreeCAD.
Thank you.
So about the Rhino users, how many computers do we have? How many computers with Rhino do we have? 3?
You need to come closer because it's easier to...
Okay, 4. I can maybe go around and do like a mini tutorial with each one if you want.
Oh, with each one.
We will start with...
we will start with Anastasia.
Yeah.
So
Okay.
about FreeCAD.
Yeah, FreeCAD.
Okay, let's do the FreeCAD first. Why?
No, just a short
Can he jump the queue?
Good. Play. Okay, new file. Okay, and we will use the philosophy of. Okay, we will use the design with the volumes. So we will not make a sketch and extrude it, revolve it. We just make some volumes, like a cylinder, boxes, and we subtract and we add other agents. So first we'll try to do something like that. That we will plug it at the pot potentiometer to control the pot.
No. Hold it up. Kenobi. Yeah.
Okay, let's make a new file. Here in FreeCAD there are all these frameworks that what you want to do, an architectural schedule, assemble. No. Okay. So we are going to the part work plans.
There is no part.
Oh, is this Windows?
This is Mac.
Where there is tool marker, so we have to
No, not the tool. We are going to this here. You don't have it. Which FreeCAD? You download now the FreeCAD from?
It's okay.
Because Adi just comes.
You explain where to click because.
Yes, it's here. Here is the place that you want.
Yeah, you need to change that.
Ah.
Yeah, that is the same because if you don't put in part, so you need to take that one, adjust it, yeah, and then we change the. It's already in there, so.
Εντάξει, ένα μικρό θα κάνουμε για... Yes.
Which one do you have?
Continue?
So people don't have the same GUI. I don't know why the GUI changes from version. You have the same GUI.
There is the official site for download. I can pass it if you want.
Just assembly, okay.
Which version do you have?
I have version 0.14. So we are going to the part. And let's first design the cylinder. It's here. Okay, maybe you can see it, or you want to make it a bit bigger? It's okay? The cylinder.
The older versions are different.
Yeah. The latest. So, here's the cylinder. When you press the button, let's make a cylinder. You have a mouse? Yes, you need a mouse. So you press the middle one, the middle, the wheel, and with the right button, you can see the cylinder.
Does anyone want to do Rhino?
The cylinder has to have 2 millimeters diameter.
You need a mouse to design this. Can you pass a mouse to... If you rotate. Okay. So, at the model, here we have the model and the tasks. So we have the new part is here, is a named cylinder. So we have the cylinder. Downstairs, there is the view and the data. So, at the view you can change colors and all that, and at the data you define the dimensions of the cylinder. So it has a radius.
Diameter 6.55.
So 3.27. Okay. This data.
Okay, down there.
Okay. And
You have to double it, not to divide by 2.
The radius, that was that much.
Ah, it was the radius. So start. And height?
1 centimeter height.
Okay, this one. So we have our cylinder. And this is the big one.
Seems like I can only enter 3.27 and the 5 cannot enter more digits. Will there be a problem?
Oh, really?
That's micro.
You need a new Mac then.
Maybe press again at the field and try to write it again. I don't know why this is happening. Like you have you run it in Linux. No. So, after that, we will create a new cylinder that we want. After this, we want to create a new cylinder and subtract from the bigger one the smaller one. To plug it at the knob. So, we create. Yes. So, the new cylinder is right here now. Here is the cylinder. So, I'm here at the part. Let me make it this. So now we have the big cylinder, and with space you can make visible or not visible. So this is the new one, and this is the bigger one. So
How did you finish?
this is the second one.
Oh, we missed that.
Yeah. Sorry, we missed that step.
What? Just click. Just click. Yes.
How did you make the new cylinder?
How?
Yeah, the second cylinder.
Yes, you just press here. It's the cylinder.
Ah, so you press it again.
Create a cylinder.
The second cylinder.
The second, all the cylinders. So, and you are selected here the second cylinder that has name 001. You can change the name wherever you want with right click. Okay, now we have to change the dimensions of this cylinder. That is, to fit in the knob, it must have 3 millimeters. Anastasia, the dimensions for the...
Then this is the interior.
Ah, this is the interior.
The other, all of it around can be whatever.
Okay. So, let's make it 10 or 5 or something bigger. Now, the first cylinder is the cylinder that we have to subtract from the bigger volume. So, the other one now, we make a radius. Yes, okay. I don't like the loudspeakers. Okay, so the radius from the second cylinder is 7 millimeters, and the head can be bigger, something like 20.
We're trying just to make a knob, okay?
Okay.
Yeah, it's simple. It sounds very, very basic.
No, the second is March has the height of 20 centimeters. The other one has 10 millimeters. Okay, now we try to see the smaller one that we will going to subtract. So we select the smaller one, and we are going to edit placement. And now we can make translations of this cylinder. So if we want to move it at the Z axis, so here's the cylinder. Okay. You are going to edit placement while you have selected the cylinder that you want to edit. So you select this cylinder. This is the bigger one, this is the small one. And we are going to edit, you are going to edit placement, and you change the Z. You can select the Z, just press with mouse, and after with the arrows, move it. No, I just move it to see it, because we have to make another section of this, and after add it inside and subtract it from the whole volume. Because the pot is is not a cylinder.
Can you go through the steps? Not in details, because they're logical steps.
Yeah.
What we can do. Yes. Step 1, do a cylinder. Step 2, do another inside.
Okay.
Without describing. Without.
Okay. The other step is to create a box. This one. This cube. Another placement. Move it. This way. And this way. And this way. Because it has to be something like that to fit at the pot. So it's not a cylinder, it's you can touch the pot. No. No. No, this. So it's this one. So it has a section here to fit. The box. Now we will subtract. Okay, this is the philosophy. You can do with these three shapes now. You can do whatever you want. With the next part that is okay. Okay. No, I missed the displacement. So, in this point,
why did you do the mold between those two?
This box?
No, the other two.
This one.
The two cylinders. Why are they?
This is the big one that we're going to subtract the small one. But first we edit the small one to have the shape that we want to subtract it from the bigger one.
Is that 40 millimeters long, the output?
This one?
I thought it was 10 millimeters long.
Yes.
But you moved it 40 millimeters.
Yes, just I will move it again. Yes, just to see it now. So now we want to subtract from this cylinder, from this one, the cube. Okay. Eh? Okay, it's the cube. The placement is at the X 2 millimeters, 4 at the Y, and 21 at the Z. Okay, this is depending the potentiometer that you have. This if you will have another potentiometer or another. So let's make the philosophy of design and create volumes. Okay, now the most important point is the subtraction. Yes. This one doesn't matter now, right now, because we're going to subtract the box from this cylinder and we move it back to the bigger one.
Okay, but it's important the placement of the box in relation to the small cylinder.
They are in the same Z axis. So, so this one. The important now is the placement of the cube. So there are this one, the dimensions. Eh?
In relation to the smaller cylinder.
Yes.
Okay, so what's the placement of the smaller cylinder?
Okay. This one. Just move 50 millimeters at the Z axis. You will see that it's relative. So now let's make the subtraction. Okay. It's this one. So you first select the object that you want to subtract the other one. So the first the big one and the second the smaller one. So first is the cylinder, and with command press the cube. So you first select the cylinder and command is pressed or control in Windows, And after you select the cube. And you subtract is this one.
So this is called the Boolean operation. In Rhino, you write Boolean in order to or join or subtract. It's when you have like an object A and an object B. So you want either to make one object of the two, or to have the difference of the two, or to take the subtraction.
Yeah.
This is a Boolean operation.
So I make the subtraction. So we have this one now.
Can you explain why I can't edit? I cannot add anything that's grayed out.
I have to come and
A picture you should have. Alright, we'll call it. What do you think?
Alexandros, can you show 1 second the placement of the cylinders?
Wait.
No, there in the slides.
when the other work with the... So, we make the subtraction here.
Can you say again yourself and then the subtraction?
Yes. We have this one. We are here, so we first select the big offset, this one, and while we press command, we select the object that we want to subtract. And after, there is here the Boolean operation of subtraction. Cut, το ξέρεις.
We don't have this.
What? Is it a bit louder?
We don't have this menu. We just have the file edit.
This menu. You have to be at part workbench.
They don't have, it's an old version.
Ah, it's an old version.
Can you give the numbers?
Yes.
The numbers. Yes. Give them the numbers slowly though. Stefania, for giving the numbers.
Or to type them in view so that we know, for example, the distance.
Okay.
We have 3 shapes, give them independently.
Okay, the first cylinder. It has this radius and this height.
720.
And the placement is 0, 0, 0. The other cylinder has these dimensions.
Wait.
But this is the placement of the first...
1 centimeter.
The green one.
Yeah, the small one.
Yes? First this one.
The placement.
Yeah, the placement.
Now, the placement, they are the dimensions. The placement, no. Here is the placement. That is minus 15 millimeters. So it comes this way. Interface. Ναι, τελειώνουμε. Αυτό δεν θα το subtraction και πάμε στο Rhino, καπάκι. Αυτό δεν έχω Rhino.
How long is the little one? How long?
How long is the stick out?
It's 10 millimeters.
10 millimeters.
And
the big
this,
one is also 10 millimeters.
the big one is 20.
20.
Go to the big one. Select the big one.
This is 20, the other is 10.
Okay.
And the small one has a placement for minus 50.
And the cube?
And the cube has 10, 10, 10 dimensions and has a placement 2, minus 4, minus 21.
That's the cube placement. Write those numbers down.
Can you repeat how you subtract?
Yes, now we are.
Now, let's finish. Do we all have the dimensions and the proper placement of the 3 objects? Yes?
No.
Stefania, you got the numbers now or not?
Yeah, I have the number, but somehow they disappear.
The most important is that you can see the shapes in this way. So you can now if you change this one, so you can see the box how it's moving. Yes, you have to select them from the model here. Okay, now let's make the subtraction. First we select the cylinder from who we want to subtract, and after the cube. And we press this one. Okay.
We subtract 2 volumes now, right?
Can you give that symbol to a menu?
Yeah. So the part. Boolean cut. Okay. And now you can see that we have at the models 2 models. We have the cylinder and this one. Now this include cylinder and the cube. So now we will move this cut, this result. Okay. 2 steps and we are finished with 3 cut that we will pass and continue with grasshopper. Okay.
Yes, but we need to show the notes as well.
Ah, yes.
Which is easier.
Later.
Yeah.
Okay, now we move the cut. We put it inside this big cylinder again to subtract it from the big cylinder. So we select the cut. We are going to edit, placement, and we move it at the z-axis. So if it's going at the face-to-face, now it's inside to the other cylinder. Okay, and we press OK, and we subtract from the bigger one now the cut.
How far do you put the cube into the cylinder in order to do this boolean? We're using a different here, parallel.
No,
not parallel, it's parallel.
Yes, this is at x2, at y minus 4, and at z minus 21.
Oh, I'm all right. I've got.
I don't know, I started thinking.
Okay, and now we subtract from the big cylinder the cut. So we make the subtraction, and here is our node.
Yeah, right.
Well, that was the result. You can do this with 50 ways.
Yeah.
Wherever you want. How? Depending.
I
I think that was the more logical. So, yeah. After that, you can go to part design. And, for example, you can fill it. You can go to model, select Now you can select an edge and fillet it and change the how big you want it to be the fillet. And okay, whatever you want. This is the philosophy of FreeCAD. Okay, the fillet is at the part design where it burns, and it's here. You can see it here. Part design is this one. It has a fillet and chamfer, depending what you want to do. Okay, and after that, you can write your name, you can design a face, you can make a parametric, you can make many things. And you export the file. First you have to select this one. This is the fillet, the final result, and you export. As an STL file. As an STL. Okay, this is done. STL. And okay, let's say the desktop. We have save. Okay, and here is the knob STL file. You can open after the makerware. This is the link that Anastasia made before. And add. You can download makerware, it's free. And insert the knob. Okay, here is the knob. Here's the hole. And you export. You select which 3D printer you want. You want it to print it fast, with details, how many fields, the cells, all the properties. And you put it in a card and you print it. That's all.
Don't you want to print it upside down?
What?
Don't you want to print it upside down?
Yes, better.
Oh, no.
Okay.
Well,
We can make a simulation.
So, yes, now, okay, let's see a little bit the software of the makerware, because here there are like some values, that some parameters that we can adjust. So, we have a box. We have a big box. We can print the box empty. We can print the box full. We can print the box in 4 hours, and we can print the box in 16 hours. So these are the parameters that you can define inside the software. So when you say, here you can just scale, turn, move, look, make copies, whatever you like. You can lay flat, arrange. So you say make. And here are the parameters. So we say that this is the machine that we have, this is the material that we have, and here is the resolution. What is the resolution? The resolution is the thickness of the layer. So if I change to low resolution, it will do layer height 0.3 millimeter. If I go to standard, it will do layer height 0.2. And if we do high resolution, it will do the layer height in 0.1. So it will be fine print.
the higher resolution, the finest the print, the more time it needs to be printed. So if I wanted to print something fast, I will go and I say, okay, I want to print something fast, I want low resolution. And then if I have this box and I say, okay, I have this box that is full closed, but I want it to be empty. So I put infill 0. So this box will be empty inside. And then I will, of course, have a problem on the top of the cap of the box, because if it's very big, the distance, then the material will go like, because it will only have the wall, and then it will just fall. So if I have a big material is not big, I will put like 1% infill. What it does, it is that it calculates the volume, and then it generates the hexagonal grid automatically, the program, that it fills the box with 1% of its volume. So now we want to do it like 4 or 5%, and the shells, they are the outline. So the machine, what it does, it prints the outline, and then it starts filling inside with the infill. 3 parameters only. So let's see. It says preview before printing. So I just say export. Okay, and then there is the raft. The raft is that we want to start printing, and we tell to the machine, okay, I want to print, but please print me a base where I will print over. It's only like a safety base. And the supports, they are for 3 kinds of problematics that this kind of printing has, which is like the bridges. So I have like an U. This is a bridge. So if the distance is more than 5 centimeters, it will not print well. Or if I have something that flies, so I have to generate automatically the supports. Or I don't remember the third one, sorry. So, okay, let's export. And the visualization is, what it does is that it says,
how long it's going to take?
it will take 10 minutes, I will use 2 grams, so you know how much. Huh? And then it visualizes the raft, which is this, in the beginning, and then slowly builds up, okay? So, export. And then it creates this file for the SD card.
Question,
No.
Thickness of the shell.
Yeah, this is the. Oh, second. It's the number of shells. So you can. It's the number of the contours of the outlines, because the machine first goes outside and then it fills inside. So if you have. Is one shell. Layer is in height. The thickness is the shell. The thickness of it's a 1.75. Sorry, it's the nozzle thickness. The nozzle thickness. Okay, sorry. Sorry.
It's like a, what do you call it in English? A thread. Looks like a thread.
So it says 10 minutes, no? So let's make a high resolution now, and let's see the difference. So here it says 30 minutes. So you see, like, the lower the resolution, the faster. It's a hexagonal mess, yes. But also in other softwares for 3D printing, you can choose if you want like hexagonal, triangular, square, or for inside. Because you can have access to the code. This is like only an interface, so you don't have so much access to the code. Okay. Do you have? Who has an STL to print?
Does anyone else have a file to print? Ready?
Just the same knob again, so.
Okay. Okay.
I made lines.
Yeah.
But now I have to change them. I'll find out how to.
So if you have STL files ready to import them into Makerware and then start printing them, call me, eh? 077.
Who has Rhino? Use Rhino? I come sit next to you. Tipo dove cari? Okay, so we make we don't make this one, we make another one.
Okay.
So let's make a circle. With a center of ground 0.
But this one isn't going to be possible if you rotate it the other way.
And then this center is extruded.
So if it goes like that, 3D printed at 20. But if it's like that, it's on the bed.
And this one will be.
And now, is go to the surface where you're going to put the decoration on. With it. Yeah. So you can zoom in there.
And now over it, we can do whatever we like. This is like what enters after over. It enters like inside this one. And then over it can have like any kind of hole. We are doing
Use a cutter afterwards.
Yeah. So the inner diameter.
So now we'll see.
Yeah. I mean, I don't have my
The practical way.
I can't really.
Well, you know, there's a lot of this printing stuff going on. I think it's really great to get the products done. Is this your workshop?
My workshop, no. You see, we're just like staring at it like it's a miracle.
Well, you know, I mean, it's like watching, you know, the microwave. You know?
Yeah. Well, it's my first time I'm watching one. Are you printing something? Yeah. This is yours? I think so. Okay. And what did you create? This. Oh. like a pyramid with a knob, with a cylinder with a thing on the edge, and it looks like a pyramid.
Okay. Okay.
I mean, I didn't do it with the help.
Okay.
You know.
But you designed it in this way, or?
Yeah, with the help of the. Okay. And mine is the green one.
It's interesting to see the order in which it prints it.
Exactly.
I think you need to understand this before you create. It looks a bit glow in the dark. Fluorescent.
It will look good.
Yeah.
I think there are vertical lines on each layer, so it goes vertically.
Like a crisscross. Okay, so that's your first layer. How long does it say it will take? Do you have a time?
I don't know what kind of. No, I don't know. But it says 5%.
Oh, okay. Oh, it will take a while. Oh, look at this one.
This is fast, eh? But it's not green. Είναι γρήγορο, Πω, καταπληκτική τεχνολογία. Α, έχει και κοκκινάκι, δεν μας το βάζε.
This is nice, but this is not printed.
Καλά.
Do you know how this is played? It's Greek. Okay. Oh, okay. I was holding it upside down. Okay, yeah. Okay. Yeah, a bit like a flute. I think a flute. Yeah, oh, this is a recorder. Yes, a normal traverse.
Something wrong here.
Okay.
Yeah.
But I think this one
The layer.
This filament is flexible.
And is it like this?
Olivia, το έχασε αυτό εδώ. Τι εκτυπώνατε? Ο printer έφυγε.
Yeah, but the fast is too fast.
Το κάνω cancel,
Δεν είναι δικό μου αυτό, είναι στο sink.
Okay.
Is that a printed?
So far.
Yeah, but it doesn't play.
Oh, really? That's too bad.
Γιατί σταμάτησε το δικό μου?
Γιατί το έχασε, αυτό το filament είναι λίγο ευαίσθητο, flexible, είναι μαλακό.
Το είδα πριν σηκωνόταν τα άκρα.
Ναι, δεν κόλλησε καλά κάτω.
Το κάνουμε άλλη μια.
Είναι να το δώσω να θυμάσαι λίγο το αρχιτό και το ξαναεκτυπώνουμε τώρα. Να αλλάζαμε,
Ναι, το κάναμε.
να αλλάξουμε τα properties μήπως.
Αυτό δεν είναι το τουλάχιστον. Είναι για την κιθάρα, είναι πλάκι για την κιθάρα. Που θυμάσαι το λαιμό σου.
We have the first one.
Πώς το λένε?
It's not success.
The fine is out that one, and it's ornamented to get me on the right wide
Αυτό που έγινε είναι ότι κάνει ένα διάφορο πράγμα το οποίο κανέναν δεν έκανε. Έχει κολλάει το χαρτί και το πάει σε άλλη μύτη και το κολλάει και να χαλάει.
Oh, that's okay. So it's all combined.
Είναι η βάση του χαρτί, αυτό ξεκολλάει. Πρέπει να βάλουμε άλλη βάση.
Πού το έχεις το αρχιάκι σου? Το όνομά σου είναι
Στέλλα.
Στέλλα.
Μέσα στο flash disk, μέσα σε αυτό το φλασάκι. Και λέγεται first.
Ναι, εννοείται.
Μάλλον στο fab 1 είναι.
Στο fab 1.
Ναι, το first. Ναι, ναι.
Και αυτά τα έχετε κολλήσει μετά με κόλλα.
Well, actually, recorders are plastic.
Ναι, με κόλλα.
Primary school.
Όλα στιγμές. Δεν μπορεί να μπει μέσα.
Okay.
Μπαίνει, το καινούριο design θα είναι να μπαίνει μέσα.
Και αυτό παίζει τώρα.
Παίζει. Τι να δω, δεν μπορώ να παίξω.
Θα δεις.
Έχω καταφέρει να βγάλω έτσι.
Α, δουλειά μου.
Αλήθεια.
Τώρα έχεις ένα τάσκ παραπάνω.
Δεν έχω καταφέρει.
Ωραίος.
Δεν έχω βάλει ποτέ μου.
Ας φύγεις τα φίλη, αυτό ρε.
The idea of having it is so it smooths out the way. Airstream.
Ναι. Αυτό μου πει και εμένα. Μία φορά
Που θα βγάλω με το καβάλι. Αυτό είναι διαφορετικό στο
Για βγάλε εσύ.
Δείτε, εγώ είπα ότι είμαι musician.
I think if you just filed it, maybe
A sound. Okay, I've been doing it incorrectly.
This is not the printed one.
No.
No.
That's why it's...
Can you teach
No, it's also...
show me how to blow in it? You just...
It's you make with your lips, you cover all this,
Yeah.
and you blow at this angle.
Okay.
It's like a bottle, but in a different way.
Because I play the flute, but it's totally different.
Yes, it's different.
Okay, let's...
Different.
Αυτό πρέπει να φτιάξει, αυτό εδώ παίζει. Αυτό μάλλον θα
You can continue with your designs, but we started printing because we want to also assemble them on the boxes we made for you and start making some sound. Yes, that's the ultimate goal, but we have less than an hour. So we cannot print everything, we start with printing some of the designs.
Yeah, well, each 3D printer has got a different one. Normally they have MakerWare, but Ultimakers have got something different, which is again downloadable and free to use. Okay, so it says, do you want to scale it up? The object seems very small. I'll keep the size.
Keep the size and see if it...
Yeah, it's quite small. Let me try with my...
It's very difficult. Maybe we had the wrong units.
Yeah, let's see.
I'm hyperventilating.
Let's open it.
Yeah, you have to twist it.
Oh, it's in millimeters.
It's like a crooked.
Okay. Now, what I want to do is I want to design
That's enough, please?
Settings, centimeters. Okay, model unit centimeters.
Yeah.
And the layout is like centimeters as well. And then I'll export it again so that I understand. Okay, so I'll just save it so that it saves there. I was to save it as a private file.
What I'm doing wrong?
Overwrite it.
More low.
Now,
Not try to do
it should be the right size?
It should be the right size.
You didn't have to manually rescale it, all you did was set the...
So the unit size.
Yeah. That's the old Filmium?
The shape of the mouth.
Open.
Is it the correct one? Oh no, that's right. But that looks huge.
Yeah, that's, we should be blowing
Yeah, that's
up
the edge for not setting the right parameters in Rhino.
Most of I think, I'm not playing with them. But I think that
now it's guesswork to try and make it this size.
No, on the edge.
on the edge, half and half. Okay.
Let's say that, you know, to do it in a bottle, it's easy. But here you have to do it, maybe going a bit more out here, I think.
Can we specify it so that it's now 4 centimeters and just scale it to that?
You're playing it like a flute. I think.
This one. So, probably.
But they say that the big one is not very well.
Okay.
That was a good one. Maybe it's because I use software.
Φοβάσαι, Αλέξανδρε.
Yes.
Το κάνω.
Τι θέλει να φέρει συνεπού.
Για τον ρόλο θα κάνουμε ένα controller. Αφού όταν το κάναμε, το κάνουμε, το κάνουμε στο θα σου άρεσε να πας να σχεδίσεις πράγματα.
Let's make a part now.
We still have started with the part because it's easier.
So you press a mesh format and you put the extension dot STL.
Not even with interaction.
Do you have something? Θα πάρετε η κάρτα να βάλουμε κάτι άλλο.
Τώρα να βάλω πρώτα.
Yeah, we'll take it to
You have
another software
I'm missing my mouse.
This mouse here.
That's my mouse.
Okay. Yeah, I trained myself off the mouse because of exactly that.
So much nicer. Okay, so.
And the holes are bigger.
Yeah.
I think it's the length that is
It doesn't matter really.
Well, look at the difference between the thumb and the first finger. It's like this. I can hardly read.
When you can set up to be the right size from the beginning. Here we start.
So I guess you did all this when you're doing architecture. You had to learn to be very good at using CAD.
I didn't learn.
No.
It's the one.
But there is a nay here.
Yes, there is one.
Why not then? Okay, so we'll go back to the
There is a difference. It's much easier to do it with the wooden one. The sound is more.
Okay, I have to try. I didn't
But I mean, 40 euros. So why buy 1, 2, 3D?
Τι να πάρω φωτογραφία, να πάρω κάτι που να μ' αρέσει εδώ μέσα.
Καλά δεν λέω.
Καλά δεν το κάνουν
If you want to buy one, or you can make your own file if you want to spend a lot of time. But why would someone use someone from plastic? Made from plastic?
Instruments and we've been trying to play this.
For the finger for the first step.
Yeah.
This is
Australia.
Measurement.
Yes.
The normal according to the window, let's take any more info down, the 3D. Like that, not like that. Okay, let's export that.
change the STL. I export to the files that
Now I know
Somebody's making it now.
We're making it now. So do you want to start on the electronics part?
There's also Raphael.
So this is like the security. If it gives you an error, you cannot print it. So you know here is an error. This is security, the last step of
those two Japanese.
You're gonna just give us. Yes, we can do it. But if you want to do it, if you want just a souvenir.
Anastasia, is this one working okay? Totally not.
We'll chat